In this lesson, we're going to start to look at ideal voltage amplifiers. To this point, we've calculated voltage gain for a number of amplifier topologies, but what we're going to start to look at is what makes an amplifier an ideal voltage amplifier, and how do we start to create those types of amplifiers in CMOS and bipolar technologies. So an ideal voltage amplifier has a voltage gain, V out over Vn, is equal to some AV or voltage gain. And what we want to see is that the source and load resistances don't influence the gain. So let's imagine that we have a generic amplifier. We'll just draw this with our typical amplifier symbol, where we have a voltage gain AV, and looking into this amplifier we see a resistance R sub I, the input resistance of the amplifier, and coming out of the amplifier we see an output resistance R sub O. Okay, so I'm going to draw another triangle to represent what happens if the amplifier isn't so ideal. So here AV is an ideal amplifier that has a voltage gain of AV, and we have an input resistance and an output resistance to this amplifier. And so let's imagine that we have a voltage source that has some input resistance, or some source resistance, R sub S. So this is our voltage source with a resistance R sub S. And imagine that we have a load resistance that we're trying to deliver some voltage signal to, V out. So if we write an expression for the total gain of this amplifier, V out over Vs, we would see that the total voltage gain would be Ri divided by Ri plus Rs. We have a voltage gain at the input of the amplifier, times the voltage gain AV of our ideal amplifier, times RL over RL plus R out, which is a voltage division at the output. Now we'd like this term to go to unity, and we'd like this term to go to unity. And we see that the input term goes to unity when Ri is equal to infinity. And we see that the output term goes to unity when R out is equal to 0. And so essentially what we're saying is that we'd like to eliminate the voltage division of the input and the output, and the way to do so would be to make the input resistance infinite and the output resistance 0. We're going to find that ideal operational amplifiers are the backbone of analog design. And if you remember the properties of your ideal operational amplifier, the input resistance was very high and the output resistance was very low. Now, of course, in practice we can't get real ideal amplifiers, but we can come close. So we use op-amps as analog computers. In past classes you might have used such amplifiers as integrators, differentiators, summers, and for derivatives. So we can do addition, subtraction, integration, derivations, etc. And of course we also use them in sample data systems. What do we mean by sample data systems? We have digital to analog converters, or DACs, and we have analog to digital converters, or ADCs. And of course, these are used when we want to go between the digital and analog domains, for computing, for instance. We also use them for filters and for instrumentation. So in the next part of the lesson, we'll start to look at operational amplifiers, and our operational amplifiers have a differential input and a single-ended output, and we will start to see that.